Alright, here's a problem for a snow day. So Nora and Joey are sitting on a sled at rest atop of a hill. Their father pushes them with a 15 Newton force over 1 meter. They slide down the hill on the sled. At the bottom of the hill, they slide for 12 meters before coming to rest. What is their speed at the bottom of the hill? What is the coefficient of friction? Alright, so our system is going to be Nora and Joey, along with the sled. If we want to consider gravitational potential energy, we will also consider the Earth. You want to see too? Can you say hi? Say hi. Say hi.
Hi.
Okay. And the sled. Daddy's talking. Alright, so we're going to look at the bottom of the hill to answer part A. So we'll start at the top of the hill and be A. Right at the bottom of the hill will be B. And in this part from B to C there's friction. Okay, so there's no friction from A to B. And then there's going to be friction. Yes, Nora?
That will be
Alright, hold on a second. Okay, so we're going to go from A to B. If Nora, Joey, and the sled and the Earth are all in the system, we will have gravitational potential energy. So we're going to have kinetic energy at A, which is going to be 0 because they start at rest. Gravitational potential energy at A plus the work done by their father will equal the kinetic energy at B plus the gravitational potential energy at B. So if we draw a bar chart here, most of this is going to be gravitational potential energy at A with a small amount of work done by their father, probably less than that. Okay, will equal the kinetic energy at B. Alright, so we're going to have mg y at A plus the work done by their father is equal to 1/2 the mass of them at B, or the mass times the velocity squared at B. Okay, for the mass of the entire system, okay, it would be Joey plus Nora plus the sled, which would be 30 kilograms. So, if we calculate the gravitational potential energy at part A, we'll get okay, so minus the trains going across the wooden floor, the gravitational potential energy at A would be 1500 joules. The work done by the floor would be 15 joules, and that will equal the kinetic energy at part B. So this would be 1/2 times 30 kilograms times the velocity at B squared. When you solve for the velocity at B, you end up getting 10 meters per second. Okay, I think technically it's 10.05 meters per second, but we'll round to 10 in this case. Alright, so now going from B to C. So from B to C, we're going to not only include Joey, Nora, the Earth, and the sled, but we're also going to include the snow in this part. Now the reason for this is they're asking for the coefficient of friction. So the interaction between the snow and the sled is where all that kinetic energy is going to go. It's going to go to internal energy. So we're going to look at the kinetic energy at B plus the gravitational potential energy at B plus any work done between B and C is equal to the kinetic energy at B plus the gravitational potential energy at B plus the change in internal energy. Alright, so they're going to slide 12 meters before coming to rest. So they're moving at the start at 10 meters per second, which will give us a bar of kinetic energy. Then they slow to rest, which will transfer all that kinetic energy to a change in internal energy, increasing the temperature of both the sled and the snow. So we're going to have 1/2 times the mass of them times the velocity of v is equal to the force of friction times that 12 meters it takes for them to stop. Alright, so substituting in for the force of friction, we have mu times the normal force, which in this case, if we look at this, would be mg because the surface is flat. So the normal force will equal the force of the earth exerted on them times 12 meters. And that will equal 1/2 mv squared. Alright, if we solve for mu, we substitute all our numbers in and solve for mu, we find out that this will equal 0.42. And that would be the coefficient of friction. Well, hope this helps solving any problems. Feel free to email me. I'll be around all day playing with these two. And enjoy your snow day.